Yeah, Murat.
Okay, let's get started. So this class will cover type 1 wind turbine systems. So this is basically the induction motor, right, with some things wrapped around it. Okay, so partly this class will be a review of induction generators, induction motors. Then we will look at sort of what kind of equipment can you put around it to make the wind turbine more friendly to use. Okay. So as a reminder of type 1 wind turbines, right, all it is has a induction generator connect to the grid. Okay, so you can think of this as a turbine. Or you can think of this as this is a turbine. Okay, so this is part of the turbine. Okay. So it's just an induction generator. So for induction generators, we have the following equivalent circuit, right, which we have seen last class. As a reminder, let's go through what the equivalent circuit looks like again. Okay. So we always have a grid voltage, VA1 here. Then we have some stator side resistance, stator side reactance. There may be a shunt reactance called XM. There may be a shunt because this comes from a transformer. So there could be a shunt element. Then we'll have X2 prime, R2 prime, and a developed voltage. Right? And this VD is really the right. This VD really comes from the fact that I have a negative resistance. Right? So I developed a resistance. So here RD is R2 prime S1 minus S. Okay, so I have when the slip is negative, I basically have a negative resistance, and this acts like a voltage source into the circuit. This is a voltage source, right? So what you can think of is we're getting mechanical power. Right? We're getting mechanical power to the from the blade, and this creates a negative slip, and this creates a negative resistance, and we generate power from this circuit. So when you look at the circuit, right? So this XM, so you compare the size of XM and X1 or X2. How does the size of XM compare to those? Right? So when we're doing calculations, often we don't work with this circuit because there's a shunt element. Okay? There's a shunt element, this XM. So how does the value of XM compare to, say, X1 or X2 prime? You remember? Which one is larger? You know, all these things. Right? So if you look at this diagram, so it's a shunt, right? So often we'll assume XM is larger. Okay, X1, X prime is much, much larger than the other reactants in this circuit. So if we make this assumption, when the shunt value is very large, what does that look like? When the shunt value is large, what can we pretend the circuit is? Anybody recall? So what's the simplification we can make? If say xm is very large in value compared to x1 and x2 prime.
Do we
Remember?
just ignore the XM?
Yeah, ignore the xm, right? This looks like a open, right? So we'll often ignore xm. And we'll often just ignore the fact that we have a shunt because the value is so much larger than the others. Right, so this is an assumption we'll often make. So if you look at the homework questions that's posted today, I think most of them, except one, says, assume xm is ignore. And the one of the homework questions basically asks you to compare the values you get from including xm with just ignoring it. And the difference in values is 1 or 2%. Okay? So often we ignore this xm. But for completeness, we often, when we draw the circuit diagram, we'll draw this shunt element. We'll draw this shunt. So if you look at this diagram, right, so this is reproduced. Sometimes we'll have external injection. Okay, we'll have external injection. For type 1, often external injection is 0. Okay, often we set this VA2 prime. This VA2 prime or S, this is 0. So physically, this is basically a current being injected into the generator. We just inject current into the generator. So what can this injection do? Anybody remember from 351? Why we have this sort of external injection here? Recall why this is useful? Right. So remember from last class, we said when you have a type 1 turbine, you cannot generate reactive power, right? Because VD is in phase or exactly out of phase with respect to the current. Right? So you can't get reactive power out of this VD. However, if you can inject some voltage or inject some current, this can be controlled to be out of phase with respect to the current. As the voltage you inject is out of phase with the current, but ideally you can generate some reactive power. Okay, so this is where we start to see how we can overcome some of the challenges presented by this type 1 system. Okay, but for now, we can assume this is 0, so assume this is just a wire. But later we'll come back and revisit. We have external injection. Okay, so for us, for type 1, let's for now assume this as a wire. Not worry too much about it. Okay, so if you look at the power flow, right? Basically, the power is flowing from the right-hand side to the left-hand side. Right, so this is the power flow we have in the turbine. Right, because we're generating, again, the left-hand side is a grid, the right-hand side is the system we have. Right, so if you look at this figure, there's a lot of power here. Okay, so we're going to try to go through this and remind ourselves what these things are called. Okay, so the first power we have, since we're coming out of gearbox, this is called P gear. Okay, so P gear is a mechanical power you get from the gearbox. Okay, from the gearbox. So there is some loss, right? When you get the power from the gearbox, there are some conversion efficiencies. You don't get all the power from the gearbox. So this loss shows up as PD. Okay, so we have a developed power. Developed power is the electrical power that you get once the mechanical power from the gearbox is converted to electrical. Okay, so this is our power. For over this resistor, what we call this is PCU2. Okay, this is PCU2. So this stands for the power loss over this resistor. right? This is our power loss. Anybody remember why the subscript CU? Remember why it's called PCU too?
For copper loss.
Yeah, for copper loss, right? So we're just assuming the wire is made of copper and we have some loss, right? So that's one power we have. Then the power going from the rotor to the stator, this is called the air gap power, PG, right? This is the power that crosses the air gap between the spinning rotor and the stator. This is PCU1. We lose some power over the first resistor. Then this one is either called P1 or P out, and the power you finally get out of the system. Okay? So there are several powers we can talk about in this system, right? We have the mechanical power from the gearbox all the way to the output power. And often in your homework or in the exam, where you'll be in a question will say find some power, and it's important to know what power refers to what. Okay, so what's the developed power? What's the air gap power? What's the copper loss? What's this? Right, so it's important to be familiar with the terminology. Okay, so none of this is very difficult to compute, but we do need to know the terminology here. Any questions about this?
I have a question.
Yeah, go ahead.
Is PD the loss or is it the power after the loss?
This is power after loss. This is the power you get.
So that's P gear minus P loss.
Yeah, so that's right. Yes.
Okay.
Yes. Okay, so let's be clear. So the copper, this are the losses, right? They are the loss. Then PD goes to PG, goes to P out. Right, so this is the power transfer sequence. So each step we have some loss associated with this, with this step. Any other questions? Okay, so this is a figure again. So for this class, since there's a lot of formula, a lot of figures, so everything is drawn twice. Right? So in case my handwriting is not that clear, this finger is drawn again. So now comes the fun part, writing down all the equations for all these powers. Right, we have a lot of powers, so let's write down some equation for these. Okay, let's write down some equations. Okay, so let's go one by one. Okay, let's go one by one. When we start, let's say we have the P gear. Okay, so we start with the power from the gearbox. This splits into two parts, right? This splits into two parts. One part goes to something called P rotation. This is the rotational loss. Okay, this is just the power you lose because you have a rotating mechanical mass. So this is the loss in mechanical power. The next, so the rest, right, the useful part, that's not lost as PD. This is the developed power. So when we look at PD, we're only accounting for the active power, right? So it's important to remember that when we write down these powers, we're only talking about active power. So if you look at the developed power, we have 3 VDIA2 prime. Okay, right? So this is 3 times 3 because we're talking about 3-phase system. VD times IA2 prime is because we have voltage times current. So do I have an angle here? So does the angle show up here? Right, so normally when we look at this kind of circuit, we need to talk about angles between voltage and current. So what is the angle between voltage and current here? What is the angle, right? So we have a circuit with inductors, resistors. So typically we need to multiply voltage and current as complex numbers. So what happens here? What is the angle between them? What's the phase between the developed voltage and the current flowing through it?
Isn't VD and IA2 180 degrees out of phase?
Right. So they are exactly right. So they're aligned basically, because there's no you cannot get reactive power out of it. Okay. So we're not going to work. So the angle basically creates this -3 RD IA2 prime square. Okay, because they're aligned in angle, right? Or they're 180 degrees out of phase. So we have a minus sign in front of this. Okay, so this is -3 R2S 1 minus S IA2 prime squared. Right, so this is the developed power we have. Right, so if we can figure out the current, if we know the slip, we can figure out how much developed power we have at this point. And this is equal to the developed torque multiplied by the rotational speed of the turbine after the gearbox. Right, so this is so at this point we have omega-2. This is the rotational speed. Okay, so we can relate the developed power, right, which is measured in watts, to the developed torque, right, which is sort of the force unit, right? So power is torque times rotational speed, or so this is, if we ask for the torque, then we can divide by the rotational speed to figure out what is the if we know developed power, we can figure out developed torque. Vice versa, if we know developed torque, we know the rotational speed, we can figure out what the developed power is. Okay, so this is an important relationship to know. So after this point, this again gets split up because we have the copper loss. Right? We have a copper loss. Then we have next we have the air gap power, PG. This is the power that gets transferred to the stator side. So if you look at PG, this is basically just subtracting these two numbers. We would get as -3 R2 prime S1 minus S. Sorry, not 1 minus S. What we get is -3 R2 prime over S I2 prime squared. Okay, that's I2 prime squared. And this is, in mechanical terms, this is the developed torque times the synchronous speed. Okay, so what you can think of is you have some developed torque. So the machine creates some developed torque. Okay. At the rotor side, you're spinning, right? At the rotor side, you're spinning at the rotor speed. At the stator side, since we have a fixed synchronous speed, this torque shows up at the synchronous speed. Okay, so you lose a little bit of power. The power you lost is because the rotor speed are faster than the synchronous speed. Okay, but you can think of this as a torque being transferred. And the torque at the stator side is just the mechanical torque. The power at the stator side is mechanical torque multiplied by the synchronous speed. Multiplied by the synchronous speed. Any questions about this? Okay, so if you compare, the equation for PD and PG, we get this as PD 1 minus S. This works out this way. You divide the above equation by 1 minus S, you get the equation for PG. So this is an important trick to know, right? If you know the air gap power, or you know developed power, and you know the slip, you can directly relate them to each other. You don't need to go through the current again. Okay, they're related by a function of the slip. Any questions here?
Just real quick,
Yeah.
could you explain again why IA2 and V out are 180 degrees out of phase?
Out of phase? Okay, sure. So if you look at this voltage, right? So let's go up. If you look at this voltage comes from the fact that you have a resistor, right? So we have a, this comes from the fact that I have a developed resistance, right? I have RD. Okay, so my developed resistance is R2 prime S1 minus S, right? So S is a real number. Right? S is some real number, R2 prime some real number. So this is just a resistance. And the current, what you can think of as I'm pulling current out of this voltage, right? So this voltage has to be equal to the current times a resistor. Okay, so if the voltage is current times the resistor cannot introduce a phase shift, right? So that's cannot introduce a phase shift, except that here the direction we're measuring the current, right? So if you look at the current is being drawn out this way from VD, right? So VD is, we have a plus minus, this way. So I'm drawing current out of it, right? I'm drawing current out of this voltage. So it has a minus sign, right? So I'm drawing current out, has a minus sign, but there's no other angles because it's a current multiplied by a resistor. Does that answer the question?
Yeah, I think I'll just have to look at it a couple more times before it really sinks in.
Yeah, so yeah, this is the important part actually to understand why there's no, why they're in phase, so why there's no reactive power out of this, right? So again, if you look at the circuit diagram, right? So what you have is, just look at this part, right? So really what you have is, you have this RD, right? And you're pulling current out this way. Okay, we're pulling current out this way. And we're asking what is the voltage across this resistor? This voltage is basically VD, right? So physically, if you want to think about it, you can think of, because there's a speed difference, there is some load, or in this case, a negative load, right? Because S is negative, so there's some sort of load or negative load developed here. And for the voltage, we're gonna say the voltage across this load is the current times the resistance, right? That's just the way, that's how we define voltage. Okay, it's the current times resistance. Because this is a purely resistive load that develops, or a negative purely resistive load that develops, there is no, you cannot generate reactive power out of this source. Okay, so if you have a motor, if you have a spinning motor, right, you have a shaft that spins, this looks like a load, and this load, or a generation, this is purely resistive. It's all active power. There's no reactive power can get out from this.
Okay, so it's basically just because current is flowing through there, and normally it goes, the direction of current goes
Right,
plus
yeah.
minus. In this
Yeah.
case, we're taking it as the opposite side, so it's 180 degrees out of phase.
180 degrees, right? Yeah,
Okay.
so, yeah,
Thank
so so it's important that the more important thing to remember here is there's no reactive power. Right? That's the important thing. Is you cannot get reactive power out of this developed voltage, or this developed, right? You cannot get reactive power out of this turbine. Okay. So if you look at this sort of power flow diagram, there's no reactive power coming out of the gearbox. Right? There's no reactive power coming out of VD. Okay. So all the reactive power ever in the circuit has to be supplied by the grid. Okay. So that's one thing that we have to remember. So when we're accounting for this active power flow, one thing you can think of why we don't account for reactive power is there's no reactive power coming out of the gearbox. Okay, just sort of all active power, and so we're looking at active power transfer. All right, so once we get back to air gap power, we have another loss. 1, 2 mixed up. We have another loss through the first resistor, or this resistor on the stator side, and then here we have the power output to the grid, P out or P1. Any questions about this diagram? Okay, so this will be a very important diagram to know where to find it. Okay, so this again reproduced here with all the equations. You need to know where to find this diagram. And this will be from now until for sure the midterm, you'll be continuously looking at this diagram to figure out what power is what. Okay, so it's very important to remember this power flow chart. All right, so if you look at this power flow chart, again, what we have here is I have a shunt element, right, between the stator and the rotor. Okay, so often we want to have a reduced model. And there's two ways to do the reduced model. One way is just to completely ignore the fact that we have a shunt. Another way is to do a 7-day equivalent. Okay. So we ignore it, then of course it's easy. We can just forget that we have this shunt resistance. But what we can also do is we can move this to a 7-day equivalent model. Right, so this is our stator side of this circuit. Right, so I can always make this in the 7-day equivalent. So I have a 7-day equivalent voltage, some 7-day equivalent resistance, some equivalent reactance. Okay. Does anybody remember how to do the 7-day equivalent? Like how do I find the, for example, the impedance? I'm sure we all have heard of 7-day equivalent before, but do you remember? How do I get the, let's say, that's the equivalent impedance? Anybody remember the formula? What is the assumption we make when we compute it?
Don't you do like open voltage or open circuit voltage, and then you Thevenin is equal to the voltage across the open circuit, and then you short circuit the current, something along those lines.
Right. Yeah, so you open circuit something, you short circuit something, right? So let's do the voltage part, right? So it's correct that when you look at the equivalent voltage, you basically open circuit, right? So you forget the fact that you have a rotor on the other end. You keep that circuit as open circuit. Then what you have is this is, because now we're just looking at the current flowing through, right? We're just looking at the current flowing through this element. So the current flowing through this element is, right, so it's JXM multiplied by the current flowing through this element will give us the equivalent voltage, right? This is open circuit voltage. So this current is easy to compute. This is just VA1 R1 plus J X1 plus XM. So this is the 7-day equivalent voltage. As you open circuit the port, and you figure out what the open circuit voltage is. Right? The voltage is just impedance multiplied by current. Okay? And the equivalent impedance, as you short circuit, right? You short circuit the voltage and you look inside to figure out what the impedance is. So we basically have a parallel. We have XM in parallel with R1 plus JX1. So if you do the calculation, X1, R1 plus JX1 plus XM. Okay, so this is our 7-day equivalent. Okay, this is our 7-day equivalent circuit. So sometimes if we want, we can reduce this to something equivalent to model the system more accurately to include the shunt, right? So if we do this, again, we just replace VA1 by VTH, replace the impedance by this sort of lump impedance ZTH. Any questions? Okay, so what we end up is we end up with this type of equivalent circuit, right? So we end up with this type of equivalent circuit. And again, you can write down all the equations for this kind of equivalent circuit, right? So if we really want to do is we can combine all the impedances here. So let's say that we have some R equivalent, X equivalent, and the develop voltage on the other end. So this is just the Thevenin plus the rotor side. This is similarly, okay? And then we can compute the, voltage and current, right? So we can compute the voltage and current. So if you look at these equations, we have IA2 prime. So here we're going to do all the calculations in complex numbers. Okay, we're going to do this in complex numbers. So I have IA2 prime. This is just VD minus VTH, right? Because we're forcing the current to go this way. Divide by REQ plus JXEQ. Okay, this is our current. We have VD as minus R2, minus RD times IA2 prime bar. Okay, so this is complex numbers. So this is minus R2 S1 minus S IA2. So the nice thing here, if you look at these two equations, basically I have an equation relating IA2 and VD. I have two equations relating IA2 and VD. So what I can do is I can directly substitute, right? I can get an equation, I can eliminate VD or IA2. Right? So what I can do is I can write things like I can eliminate VD using the two equations I have above. If you do some calculations, you'll figure out this is IA2 prime minus VTH over RTH plus R2 prime over S plus JX equivalent. Okay. So you do some algebraic manipulations, well, you will get this kind of equation. So the nice thing about this equation, right? The nice thing is when you solve this type of problems, what you know is the Thevenin equivalent voltage because that's given by the grid voltage and the stator side parameters. So that you know RTH, you know X. Okay. You also know the slip because the slip is what you measure. Slip is given by the speed of the rotor. Okay. So you know these two. So you can directly compute IA2 prime. Okay. You can directly compute the complex voltage. Okay. So VD, we can eliminate VD because I have two equations relating IA2 prime to VD. Okay, so from these equations, I can directly get the equation for IA2 prime. And this right? And for example, if I just want the magnitude, so this is just the magnitude, then I have VTH. RTH plus R2 prime S squared X equivalent squared, right? So this, once we get down to this equivalent circuit, we can do sort of a lot of calculations. Okay, it just is not different than any sort of normal calculations we do for this kind of circuit. Questions?
I was wondering, why are you using the subscript A2?
Oh, A2, A is for a single phase, so we're talking about phase A. 2 says that this current came from the rotor side. So that's a
Oh.
2, right? So this is a single phase equivalent, this is a single phase current. And the 2 is this is current coming from the rotor.
Rotor side, okay.
Rotor
Thank
side,
you.
yeah. So the prime is again reflected to the primary side. So that's the notation we have. Okay, so remember, when you plug this equation, when you do calculations, be careful to look at whether the voltage is line-to-line voltage or line-to-neutral voltage. Okay, in all these calculations, the voltage are assumed to be line-to-neutral. So. Okay, so, but in most problems, you're given line-to-line voltages. So remember to divide by √3. Okay, remember to divide by √3, right? Because again, this is a single phase equivalent current. Any other questions? Okay, so you'll see this a lot, right? So this works, for example, this week's homework, you'll see quite a number of questions like this, asking you to do induction machine calculations. All right, so this is just repeated calculations. The next is the interesting thing, that's the speed torque characteristics, right? Because if you look at power, so where did power go? Okay, so if you look at all these power equations, right? S is a part of this equations, right? So you have a slip. Right? So we know that slip being 0 means that you're not generating power. Okay, so you need slip to be negative to generate some power. But as always, for us engineers, what you want to do is you want to optimize, right? Then if you know, okay, some negative S generates power, the next question engineers ask is, what S generates the maximum amount of power, right? So what is the most efficient, right? What is the maximum power I can generate out of this? Because for sure the power depends on the slip. Okay, so speed torque characteristics tell us, how does a torque and in turn power look like when we vary the slip. Okay, we want to know what that relationship is. Right? So if you look at speed torque relationships or speed power relationships, what we have is something like this. So let's look at the equation. So if you recall, our equations are power, developed power, minus 3 R2 prime S, 1 minus S, IA2 prime squared equals to the torque times the rotor speed. Right, so W omega 2 is the rotor speed. So the developed torque, you just divide by omega 2. Right? This whole thing divided by omega 2. And there's 2 ways to write this. One is just minus 3 R2 prime S omega 2, 1 minus S IA2 prime squared. This is one way to write it. But another thing we can recognize is recall omega 2 divided by 1 minus S. Okay? This is equal to the synchronous speed. So let's write this equation first. Now explain. Okay, so if you keep writing like this, what you can do is you can collect the terms together, and we have 3 R2 prime S omega S. So instead of the rotor speed, we can talk about things in synchronous speed. Right? So things in synchronous speed. And this is IA prime square. Okay? So both are equivalent way of writing it. You can either leave the 1 over S outside or leave the 1 over S inside. So what we have is omega 2, 1 over S equal to omega S. It's by the definition of slip. So you plug in the definition of slip, you figure out this is the equation that we have. And then if you look at the equation we have for IA2 prime, right? We have some equation for IA2 prime. This is some equivalent voltage. RTH plus R2 prime S squared plus X equivalent squared. So we're going to combine these two equations together. Okay, so I have an IA2 squared in the TD equation. So we're going to plug things in, and we're going to do some manipulations. What you get is the div of torque is -3 R2 prime S omega S VTH squared RTH plus R2 prime over S squared plus X equivalent squared. So this is a torque relationship we have, right? So basically this says if you're given the slip and you know VTH, which is given by the grid, you can compute the amount of torque. You can compute the amount of torque we have, right? So this equation, looks, at this time fairly complicated, but it's interesting to try to plot this and see what it looks like. Okay, so let's try to plot what this looks like. So let's say this is speed, okay, and this is torque. Okay, so let's look at the speed torque relationship. So speed is the rotor speed we're spinning at. So what is the torque when you're spinning right at the synchronous speed? What torque should we get? Right, so we look at this equation. So intuitively, without looking at the equation, if we're spinning at synchronous speed, how much torque do we get? 0, right? Should be no torque. There would be synchronous speed. So from this equation, why do we get 0? Do we get 0? Let's look at if our equation makes sense, right? I just wrote down this equation and said, you multiply a bunch of things together, it comes out this. Is it true that when S equal to 0, we get this? We get 0? Right, so it's a little bit subtle, this equation, a little bit subtle, because you have a 1 minus S sitting in the denominator, but you have in the denominator itself, you have a 1 minus S squared. Okay, so you're dividing by S, but you're also dividing by 1 over S squared. Okay, so when S is very small, basically the square term dominates, and that becomes very large. Okay, that becomes very large. So at S equal to at synchronous speed, you get 0 torque. You get 0 torque. Then as your speed increases past the synchronous speed, we pick up. Okay, we pick up speed. But then when S keeps going, right, when you increase the speed more and more, what happens is when you increase the speed more and more, you have this 1 over S term. Okay, so you have this 1 over S term. As S grows, 1 over S gets smaller. And this term will start to dominate, right? So then the speed torque relationship goes something like this. So it says as you start from synchronous speed, 0 torque, the torque kicks up fairly quickly. The torque kicks up. This is because you reduce the influence of this 1 over S squared term. So you reach a maximum. Then the 1 over S term starts to take over and the thing goes down again. Okay, so we have a graph that looks like this. So what we have is so this value, this is called the pull out torque. Right, so this is called the pull out torque. This is how much torque I can pull out, and sometimes as TPO. Okay. And this is omega PO, omega pull out, and this means the maximum, the speed that you generate the maximum amount of torque. Questions? Okay, so this is torque we generate, right? So if you look at this and drawing this again, a little bit nicer plot as we got something like this. Okay? So there is a maximum torque we have in the system. Right? Okay, so now I guess this is a good point to take a break. So let's take a break now. When we come back, we'll basically do a bunch of examples. Okay, so there's a lot of equations here we can use. So I'll do some examples to sort through how do I use these equations. But none of these equations are very difficult. You should not be needed to derive any of them in real time. Okay, they're all given on the slides. But the important thing is just know which one to find and which one to use. Okay, so what does, understand what the question is asking you and finding the right equation to use. Okay, so let's take a break now to 126, and we'll do a bunch of examples to see how we can use these equations. Thanks, guys. Okay, all right, so let's get started again. So for the example, so we're going to do some examples, and the first example is like this. So let's say we have a type 1 turbine, 6 poles, 60 Hertz, and spinning at a rate of 1250 revolutions per minute. And the terminal voltage of the generator is always 690 volts, and the machine has the following parameters. So we're going to ignore the core loss and the rotational loss. Okay, so rotational loss meaning that we're not going to think about the losses in the gearbox. Core loss means we're going to assume the shunt as just purely inductive. Okay. So look at ignore core loss. This means shunt is just XM. We don't have a resistance in the core. And the rotor loss means we're not losing power from the gearbox to the developed power. Okay, so I want to find the current in the rotor circuit, right? So this is IA2 prime. Right? So this is the full name of IA2 prime. Is the current in the rotor referred to the stator circuit. We want to find the developed power, we want to find the air gap power, and we want to find the power delivered to the grid. Okay? So this is a very typical example of a question you'll see. Right? So let's get started, right? So the first part is basically to find what the equivalent circuit is. Okay, so for all these problems, your first step is to figure out what the equivalent circuit is. Right, so for this circuit, for this question, we're including the shunt XM. So we need to use the full set of equations to figure out what the equivalent circuit is, right? So the first thing we do is let's figure out what the Thevenin equivalent voltage is. Okay, let's figure out what that is. So this is JXM, VA1, R1 plus J. 1 plus XM. All right, so we can plug in all those numbers. So it's my XM. This J times 2, 690. So remember to divide by √3. Okay, always remember to divide by √3, right? Because the grid side voltage, if the question is like this, the terminal voltage of the generator is 690 volts, that's the line-to-line voltage. Okay? So here, what we want is we want to find the per phase current, right? So we're going to divide the voltage here by √3 to convert to the line to neutral voltage. Divide by √3. We may just well take this voltage to be angle 0. Okay, so we can pick a reference. So let's pick this to be the reference over 0.01 plus J 2.1. So plugging all the numbers, what we get is 379.39, angle 0.27 degrees voltage. So this is our Thevenin equivalent voltage. We can write down the Thevenin equivalent impedance. Again, this is just by plugging into the formula. Not much more to say beyond that. Okay, you get this by just plugging into the formula. And then we want to compute what the slip is, right? So slip is the synchronous speed minus the speed over the synchronous speed in RPM. So this is a 6-pole machine, right? So 6-pole machine is 1200 RPM. Right, so again, we can use a formula, right? So we can use, if you want, you can use this formula to figure out what the synchronous speed is. 120, so 120, the frequency, 60 divided by the number of poles I have. This is 1200 RPM. Or you can directly recognize that since the speed is 1250, the synchronous speed has to be 1200. So this minus 0.0417. Then we get IA2. So we got the IA2 prime. Again, we have an equation for all this, VTH, RTH plus R2 prime over S plus JXTH plus X2 prime. Plugging all the numbers, we get 1.255 and go 40.23 degrees kiloamps. Right, so all this is just plugging in equations, plugging numbers. The equations are given, the numbers are given, so there's no hard thing to do except plugging all the numbers. Okay. Any questions about this or this first part? Plugging numbers. Right, so unfortunately for this part of the course, they just all those kind of equations. As this is just the way that the induction motors work. So we need to, you need to be comfortable in applying these equations. Right. So again, the thing is to remember to divide by √3. Okay. No matter how many times I say it, at least one of you will not do this in the midterm, and you'll be unhappy because you lost, 2 marks. If you forgot to divide by √3. But so please divide by √3, right? In all these type of equations to convert the voltage from line to line to line to neutral. Okay. So this is the current. Then second part asks us for the developed power. So once we know the current, developed power is very, we can calculate this quite quickly. -3 R2 prime S1 minus S. IA2 prime square. Okay. So the key thing to remember here is this is the magnitude. Okay. This is just the magnitude of the current, right? Because I'm only computing the active power. And this is just the magnitude of the current. So minus 3.1, 17, 1 plus 0.417. Right, so slope is negative squared. And altogether give you 1.18 megawatt. Okay, right. So just the thing here, just remember that this IA squared is a magnitude squared. Okay, so so a little bit tricky thing is you're doing this using your calculator. The natural tendency is to find IA as a complex number. Then square that and plug into this equation. Right, this happens quite a bit again on the exams. You just square. You saw you found IA. You got IA2 prime already. You're gonna square that and use this equation. The trouble with that is IA2 prime in the part A you found as a complex current. Okay, for the developed power you have to use the magnitude of that current. Right? So when you just square a complex number, you still have a complex number. So it's not uncommon to see a question where asking for developed power, you have a real and imaginary part for the developed power. Because you square the complex number, you didn't think a lot about it, you just put in that number. And that will be judged very harshly on the exam. Okay, so those kind of mistakes will be graded very harshly on the exam. Right? At least you should know the developed power is a real number. Right? When you ask for the developed power, you cannot have a reactive part of it. It cannot be imaginary, cannot be a complex number with some non-zero imaginary part. Okay, so that's one thing to be careful about. Right, when you square this, if you had in your calculator, to make sure square the magnitude. Okay, don't square the complex number. Right, otherwise you'll be not, you have a imaginary part, and that will be graded, very harshly. Okay, that will be treated harshly because that is something you should be able to recognize you did something wrong. Right, so root 3 or not, if you forget about divide by root 3, the answer would not seem obviously wrong. It'd be just some answer. That's root 3 times different. However, when you ask to compute the developed power, and if you put down a imaginary part, that is something where you should recognize there's a bug in your calculations, right? And that will be judged, quite harshly when I grade the midterm or the final. Okay, so that's something to remember. We'll square this, square the magnitude. Right? If you forgot, you should be able to tell that this is the wrong answer. Right, so we can look at the next part is look at the air gap power. There's several ways to do this calculation. We can just divide by 1 minus S if we want, or we can subtract off the copper loss. Both ways are possible. They will be equivalent. So here, let's just do it subtracting the copper loss in. So this is 2.8. Okay, so if you do this, you get is at the end of the day, you get 1.132. So you can do other calculations to get power C. And the last asks the power to deliver to the grid. So power delivered to the grid is a little bit tricky for this part. Because if you look at power delivered to the grid, we cannot use this equivalent circuit anymore. Because here we have a 7A equivalent circuit here. So power delivered to the grid is not necessarily the power delivered to the 7A equivalent voltage source. Okay, so that's different, right? Power delivered to the grid is different than power delivered to 7A equivalent source. Okay, so what we need to do is for this part, we have to re-expand, right? So we have to draw out this part. Okay? So what we know is we know IA2 prime. We know the complex current flowing this way. But what we want to do is we want to figure out this current because I want to compute the loss over the first resistor, right? So that's a loss I want to compute. Okay, so I want to compute that loss. So to compute that loss, I need to figure out the current, IA1 current, right? So I have a current divider, basically, right? So the two branches divide the current, and I need to figure out how much current is going to which side. Okay, so that's the current we need to figure out. Right? So the way to do this is basically circuit analysis, right? Again, all this is fairly standard circuit analysis. So if this voltage is Vm, right, if this voltage is Vm, then what this voltage does, right? So what this voltage does is this voltage satisfies Vm plus IA2 prime, R2 prime S, 1 plus JX2 prime, this equal to 0. The reason this equation holds is if you look at this Vm voltage, if you look at the rotor side of the circuit, rotor side I have X2 prime, R2 prime over S. This is both the R2 prime and the developed RD added together. I'm facing some voltage Vm, and I have current flowing this way. So this is my rotor side of the grid. So this sets up a relationship between Vm and IA2. So you can rearrange this. So we get as Vm as minus IA2 prime R2 S plus JX2 prime. And plugging the numbers again, what we get is 326.08 angle 17.6 degrees. Right, so this is Vm. Any questions about this Vm computation? Why Vm equal to IA2 prime multiplied by this number? Okay, so again, it's important to understand this type of examples, right? There's not that many different ways I can ask questions about induction generators. Right, so this example covers a lot of that. There's sort of the equations are what the equations are, and most of the questions will be something like this.
Just a quick question. I guess in this case, we can't assume that the shunt inductance is an open circuit because XM is provided.
Yeah,
so,
XM is provided, yes.
Okay. So if it weren't provided, we could just assume it's open.
Yeah, so if XM is not given, then don't worry about it. Just assume that's not there.
Okay. Okay, sounds good. Thank you.
Yeah, so pay attention to the question, right? So question give you XM, then you cannot ignore XM. Right, so in the so every question should be clear. So we should have explicitly said, if XM is giving the question will explicitly say, take the shunt into account, something like that. It should have been said. But in general, if you're given XM, you need to use a value. If you're not given XM, then don't worry about XM. Right? So if there's no XM, this calculation is much easier because you can directly use IA2 prime as a current. Here we have XM, so I have to look at how we have to divide the current. Right, so the current divides as IA1. That's really Vm minus Va1. R1 JX1, plugging all the numbers. 1.32 angle 47.31 kiloamps. And then if you look at the output power, this air gap power minus 3 R1 IA1 squared. Plugging all the numbers, what we get is 1.085 megawatt. Okay. So this is sort of a typical question you'll see on this week's homework. Right? So try to go through them, understand what the equations are. So this part of the class may seem, fairly tedious and not that difficult, but still there's a lot of equations. And if the midterm comes along and you're rushing, then it's sort of it's easy to make a mistake, right? So be sure to know where the equations, know how to find the equations, know how to use the equations. So in case you missed the class yesterday, the midterm is February 11th, right? February 11th is a full day exam. So post at 6 a.m. in the morning, hand it in by midnight, right? So that's a midterm. Okay? So if you have a conflict or if you need to do it some other time, please let me know at least a week before. Okay? So we can be flexible. You can take it if you have something that day or some other things. You can take it some other time, but do let me know at least a week before the midterm. Okay, so that's sort of one example. Another example, let's look at some limitation of type 1, right? So really after, basically the next two classes will be how do you make type 1 better? Okay, so this progress took about 20-some years in the field. Okay, there's a lot of technologies associated with how to make type 1 better. We're going to look at that, right? We're going to look at what kind of technologies are used to make type 1 better. So before that, right, let's just summarize again what's some of the limitations of type 1. Right, so type 1, the big limit, so the benefit or the advantages of type 1 are just very cheap, very easy to construct. The drawbacks or some big ones, the three big ones are this neat outside, right? Basically a neat outside flux, right? So basically need something else to provide synchronous speed. So the grid has to set the synchronous speed. Right? It cannot set its own synchronous speed. It needs a frame of reference provided by the grid. So this is needed. So there's cannot operate as a standalone system. Okay. So if you build a microgrid and your generator is a type 1 turbine, then cannot provide power. Right? Just very hard for this one to provide power. Right? So you need some reactive power compensation. Right? Another drawback is it consumes reactive power. It consumes reactive power. It cannot just this inductors, right? Have inductor in it, so it has to consume reactive power. And the third one, this thing has a high starting current. It turns out the current is sensitive to the slip. So when you connect it to the grid, it tends to have sort of this current surge, cause a current surge. So this is equivalent to being, if you have some motor that's starting, basically when you start the motor, it needs to draw a lot of current. Okay, so sometimes, let's say a breaker in your house trips, that's often because some motor started and drew too much current and tripped the protection. So this sort of induction motor tends to draw a lot of current. Right? So these are the limitations. Although being said, there are still some uses for this sort of induction generators. For example, I have talked with Amazon on one possible project where they need to use an induction generator. And the reason is because they're very space limited. So it turns out for the space constraint they have, synchronous generator is too big and they need an induction generator. And all this they can design around it. And they end up needing to use sort of induction generators to make it work. So there are still uses for induction generators. It's just you have to keep in mind these are the limitations, right? So can you provide a synchronization? Can you provide the reactive power to support voltage? And do you have, can your protection system take the surging current? Okay. So these are the limitations, right? So the reactive power part is quite simple, right? Because again, VD cannot provide reactive power. So what you have is just that all of those elements, right? Every element basically consumes reactive power. Right? So Q1, the inductor on the stator side consumes reactive power. The inductor on the rotor side consumes reactive power. The shunt inductor can consume reactive power. Right? So this shunt can consume reactive power. So if you look at the total power, total reactive power, what it looks like is this. Okay, so we'll always consume reactive power no matter what. So let's say this is the speed, this is the Q on this axis. Then at the synchronous speed, you don't consume, right? So at synchronous speed, you consume the minimum amount. Then basically your curve, reactive power consumption curve goes up like this. Okay, so remember we said the active power depends on the sign of the slip, right? So a negative slip generates power. However, if you just add all these equations up, the reactive power is symmetric with the sign of the slip. Okay, so if you go away from synchronous speed, you have to consume reactive power, right? So that says you cannot produce net reactive power. Right, so this is just a picture saying that the grid is always providing reactive power. Okay, so there must be some source of reactive power. If you can use a capacitor, you can build a capacitor, but something needs to be providing reactive power to this generator. Okay, so this is one drawback. The second drawback is called the inrush current. So what inrush current says is if you look at the current to the speed relationship, again, the minimum occurs at the synchronous speed, right? This minimum occurs at synchronous speed. But if you look at this curve is quite steep, right? So it's a curve that's going up and down quite steep. So what happens is for this turbine, you may have an operating point, right? This may be your operating point. And this may be the equilibrium you operate at. But what happens is when you first connect this turbine to the grid, okay, this may be your starting point. Okay? This may be your starting speed. So at this starting speed, what happens is you can draw a very large current. Okay? So if you have a blade, right, you have a turbine, you have a machine. Let's say your equilibrium speed is 1250 RPM. However, when you first get connected to the grid, your speed may be larger. Okay, your speed may be, let's say 1300. And what happens is you have a big rush of current through the system, and this creates a surge in current. So this is not a very graceful change in current. As if you go away from the synchronous speed a little bit, the current increases, but the current increases a lot. Okay, so this is that's why sort of you can see a lot of big current shift going up and current oscillations in the system. Okay, so this is called inrush current. Inrush means when you first connect to it, sort of the rush of current that goes through the system. Right, so we can do one example, right? We can do one example here. So if you look at this example, everything is same from before. So the same from before. Right, but here we're just, the assumption we make is when we first connect it to the grid, the spinning at a faster speed. Okay? It's spinning at faster speed. It's spinning at this speed. Okay? So you can imagine that my this wind turbine was not connected to the grid, right? Was not on, but then I connect to the grid. and suddenly I start to provide power, right? I start to provide current. Okay. Then let's look at how much, what is the magnitude of the current we have in this case, right? Compare us to say before, right? So before in this problem, our speed was 1250. We compute the current. So let's see what happens when we, connect to the grid at a much higher speed, at a higher speed. Okay, so it says, so here is basically we change S. Okay, we change S. So this is minus 0.125. Then this exact same calculation from before. So none of this changes except the value of S. Except the value of S. So we can plug everything in, substitute S from to 0.125, and we get 3.447 kilograms, right? So before, we have 1.562 kilograms. So then so this is about 200%, okay? So basically, when you first connect it, you have a surge of current that's 200%. Let's say your normal operating point, and then the normal operating current. So if you have too large of a current, what happens? You tend to trip protection devices, right? So all the protection devices we have in the grid, a lot of them work by sensing current, by sensing whether the current is large. So we have this kind of current going through. It's hard for the protection device to figure out, is this a normal part of connecting an induction generator to the grid? I have a large current, or is it a large current because of something else? So that's why you can see sort of this large inrush current as not ideal for this operation. So one thing interesting to know is, I guess we can think about is, why would the protections all sense current? Right, so all breakers in the grid, most protection systems in the power system operates by measuring the current. So why is that the case? Why are they measuring current? Why not measure something else? And they're all measuring whether there's a large amount of current going through the system. So why are the protection built that way? Why do we worry about large current, and why, instead of say no current, why do we worry about large current? Why do we not worry about large voltage? So during faults, you already have large current. But why do faults have large current? Right. So this is correct, right? So faults tend to produce large current, but why? Why do faults lead to large current? So what kind of faults do you think produces large current? Phases got short, right? So yeah, so David is writing in the chat saying that you get large current because you have a short circuit somewhere. Okay, so that's where you get large current, right? Because the resistance, the impedance reduces. That produces large current. In the system we have, the voltages are set pretty locally, right? A generator can maintain its voltage, right? You have, capacitors maintaining voltage. So what happens is you have a voltage that's fairly set. Even if fault occurs, voltage at the other part of the grid doesn't change out that much. However, if you have a short circuit fault, then you're basically, connecting, let's say, power to ground, right? Connecting sort of the positive and negative together. That causes large current. And that's the thing you want to prevent, because this causes damages. So we're mostly worried about short circuit faults. And short circuit faults leads to large current. That's why a lot of protection is set to just, trip after this kind of behavior, right? And other faults do happen, but many faults that reduce the voltage, for example, are very local faults, right? So this sort of short circuit tends to produce large current, and that's why we protect this. Okay? So If you have a turbine that looks like a short circuit fault, then that's obviously not ideal, right? It's asking a lot for protection devices to figure out what's actually going on. So there's ways to reduce this inrush current. Ways to reduce this. So can you guys think of ways to reduce the inrush current? So think back to, again, think back to 351. What devices do we have that can maybe damp out this current somewhat? Okay, so what I have is, I have the generator. Okay, so this G stands for the generator. I'm generating this sort of three-phase power. Let me just draw a single phase for simplicity. So I have a generator generating power, but my generator tends to produce large amount of current. Right? So I have the grid on this side. So what do I put in the middle? Maybe, you know, to make the current appear smaller. I remember back to 351, you did a lab on this. What device they were using the one of the labs? Or at least for the people who physically did the lab, what device they were using the lab? Right, okay, so anybody remember this symbol?
Can you put in a starting resistor? Oh.
Close, right? So putting a thyristor. So what this does is, what you can do is you're putting a switch, right? So you have a switch that controls, you know, when you want to bypass this, but then you put this kind of thyristors back to back. Right, so what they do is they limit, right? They have a triggering angle, and this triggering angle limits the amount of current that goes through this line, right? So when you first connect this to the grid, you still wanted to connect to the grid, right? You still want to connect to the grid, but you don't want the current to go. You don't want the, you know, all the current to rush through. So you connect, but you open the switch. So you have a thyristor there that limits how much current can flow between the two, and then you can close the switch once everything settles down. Right, so this thing has a triggering angle alpha, right? For example, and this will limit the current flow. Okay, so this is one way you can reduce the inrush current. As you build this kind of protection, you build this kind of circuit around. Right, so by varying the triggering angle, you can sort of set, you know, what is the upper limit of the rush of current through the system. Right, and these are, you know, power electronic devices because they have to stop a lot of current, right? So they're sort of bulky, big devices here. So that's one thing we care about, right? So another thing we care about is stability, right? It's about stability. For stability, is for this kind of system, what we always worry about, right, is you have mechanical power into the system. And this mechanical power is determined by wind. So it's some sense random, right? So you have this random mechanical power coming to the system. Okay? And then normally, right? So normally, PM equals to P out, right? So the electrical power equals to mechanical power, subtract the losses. But it's very possible that since this is a wind turbine, so you have more wind, and suddenly you have an increase in mechanical power. That cannot yet be, right? So that's not matched by the electrical power output. So what happens in this case? Let's say you have a, let's say you have a sudden gust of wind, and we have more mechanical power, but we're not outputting that much electric power. So where does this power go? Any ideas? Right. So I have a wind turbine. The wind suddenly picks up, but the load stays unchanged. So where can the power go? It doesn't go to heat, right? It's not that. So eventually it will end up as heat, but not right away, right? It's just, it cannot directly go to heat. Although that's a good thought. So hold that thought. We'll look at that next class. But now just imagine a sort of standard induction generator. And there's power, sort of more mechanical power. So where can it go? Right? You have this mechanical power has to go somewhere. So where can this mechanical power go? Right, so it has to go to the gearbox, right? So the gearbox itself cannot store power, right? So the gearbox is basically changing the rotational speed. But what happens is things have to rotate faster, right? So essentially what happens is the speed increases. Speed meaning the rotational speed, right? So because I got mechanical power, the load is now increasing, I have to go somewhere, so the blade will spin faster, right? So one way to store power is to spin the blade really fast. So the blade has to go faster. Okay? Blade has to go faster. The issue with the blade going faster is the following problem. It's following problem. So I remember if you look at the torque speed relationship, right? It goes something like this. It goes something like this. Right? So this is synchronous speed. Okay. So what? Let's say if the operating point, right? So let's say this is the operating point. Then speeding up a little bit is okay. Okay. It's okay if you speed up a little bit. You do generate more torque, and this can go and turn the blade faster. You basically just turn the blade faster. If your operating point is here, then you run into problems because no matter, right, you can't, your speed increases, but your torque or your power actually decreases. So in this case, you don't get more power, right? You cannot store more power because the faster you rotate, actually, you're losing torque, you're losing power. Okay? So this point is where you have, this is not stable. Okay? This is just not stable at this point. Right? So it's so what you're afraid of for type 1 is if you're operating, right, very close, let's say to the maximum torque, to the pull out torque. If you suddenly get more power from wind, there's no easy way to dump that power. Okay? Speeding up the blade only works up to a certain range because these are nonlinear characteristics. You cannot always dump power there. Then the interesting question is really, how do you get rid of power, right? And we don't always do it successfully. So if you look at, if you go on YouTube and Google failures of wind turbines, you see some spectacular failures. And those failures all come from the fact that there's nowhere for the power to go. You cannot dump power. So if the load stays the same and wind keeps on blowing, and then eventually things blow up. So you cannot dump power. Okay? So stability is really something to keep in mind when working with type 1 turbines. Stability is a big issue in turbine design. Okay? So we'll stop here today, but next class we'll pick up by looking at the stability issues, right? The idea of where can I dump power? Okay, I have more power from wind than I can supply to the load. That does not mean inefficiency, right? Normally we don't worry all that much. We worry about efficiency, but the loss of efficiency is not catastrophic. Instability is catastrophic failures. Okay? So we need to dump the power somewhere. Okay? So when that power causing to be unstable. So the suggestion of turning extra power energy to heat is actually a good one. So we'll stop here today. Next class, we'll look at how do we do that. Right. So basically, we'll try to again engineer things around this generator to see how do we do this type of control, right? How do we dump power as heat? Okay. So let's stop here today. The homework is out. Take a look, and see you next Tuesday.